In this lesson, we're going to continue our discussion of dirty biochemistry by talking about the Tca cycle. As a quick refresher, here's everything that we've talked about so far. In the first video, we talked about glycolysis and gluconeogenesis, shown there in the red box. When you go from glucose down to pyruvate, you're undergoing glycolysis. And when you go back up from pyruvate back to glucose, you're going up doing gluconeogenesis. In the next video, we talked about the different options for pyruvate metabolism, shown here in the red box. Remember, there were 4 different options that pyruvate could take, and one of those options was to convert pyruvate into acetyl-CoA. And that is what we are talking about today. Acetyl-CoA can enter the Tca cycle and undergo further metabolism to generate important molecules for future use in the electron transport chain. Today's video is about the Tca cycle. This is also known as the citric acid cycle or the Krebs cycle. The Tca cycle has one main goal, and it's important to keep the big picture in mind when we discuss it. The goal is to generate NADH and FADH2 molecules. The reason that you do this, and we'll touch more on this at the latter stages of this video, is to create molecules that can go into the electron transport chain and shuffle electrons to generate massive amounts of ATP. So again, just for the purposes of keeping the big picture in mind, the goal of the Tca cycle is to generate NADH and FADH2 molecules so that those molecules can leave the Tca cycle and go to another biochemical pathway known as the electron transport chain, which we will discuss in another video, to generate the most amount of ATP. Now, the overall reaction for the Tca cycle is acetyl-CoA plus 3 NAD plus FAD plus GDP plus a phosphate. And that yields 2 carbon dioxide molecules, 3 NADH molecules, 1 FADH2 molecule, 1 GTP, and 1 COA. Again, look at the overall yield of the Tca cycle. We can generate 3 NADH and 1 FADH2, and that is the main goal of the Tca cycle. Start with acetyl-CoA, and again, we started the video today talking about how pyruvate could be converted into acetyl-CoA, and this marks the first step in the Tca cycle. Acetyl-CoA will turn into citrate. Citrate will be converted into isocitrate, so you just put an iso in front. Isocitrate will be converted into alpha-ketoglutarate, and during this step, you also have the production of 1 NADH. Alpha-ketoglutarate will be converted into succinyl-CoA, and during this step, you also have the production of 1 molecule of NADH. Succinyl-CoA will have the CoA ripped off and turned into succinate. Now, it's during this step that the COA is produced. Again, remember the overall net reaction of the Tca cycle. We are producing 1 molecule of COA, and this is the step where that's done. Succinate gets turned into fumarate, and during this step, we have the production of our one and only molecule of FADH2. Fumarate gets turned into malate, and malate gets turned into oxaloacetate. It's during this step that our third and final molecule of NADH is produced. Oxaloacetate can combine with acetyl-CoA and form citrate, and the cycle can continue to spin so long as there is a stimulating factor in the body. Now let's pause for a second. This is the overall biochemical pathway of the Tca cycle. It is not important to memorize every single enzyme that catalyzes every single step. However, the one that you do need to know is the rate-limiting enzyme. That rate-limiting enzyme catalyzes the conversion of isocitrate to alpha-ketoglutarate. So the rate-limiting enzyme of the Tca cycle is isocitrate dehydrogenase. Now, if you can memorize the actual stepwise pathway, it shouldn't be hard to remember which step is catalyzed by isocitrate dehydrogenase, because the name isocitrate dehydrogenase tells you which product or which substrate is being dehydrogenated. So the enzyme is literally called isocitrate dehydrogenase. So it's telling you that isocitrate gets dehydrogenated. So therefore, the conversion of isocitrate to alpha-ketoglutarate is the step where the rate-limiting enzyme of isocitrate dehydrogenase acts. Because again, it's dehydrogenating isocitrate. So your substrate for the rate-limiting enzyme is isocitrate. Now, that is the rate-limiting enzyme, and you absolutely need to memorize it. But what also is important to memorize is what stimulates the TCA cycle and what inhibits it. ADP will stimulate the TCA cycle. The reason is quite obvious. The TCA cycle's main goal, again, is to generate NADH and FADH2. Now, the purpose of that, as I already stated, is to have those molecules leave the TCA cycle and go to the electron transport chain, where they can be used to generate massive amounts of ATP. Therefore, in the presence of ADP, which is to say you don't have ATP yet, you're going to stimulate the TCA cycle because the body wants ATP. And if the body wants ATP, it needs the electron transport chain. And if it needs the electron transport chain, then it needs the TCA cycle to make FADH2 and NADH so the electron transport chain has the molecules it needs. So again, in the presence of ADP, you stimulate the TCA cycle because you don't have ATP. And you're stimulating the TCA cycle because you need FADH2 and NADH. Now, obviously, if ADP stimulates the TCA cycle, then ATP is going to inhibit it. Because think about it, you don't need the electron transport chain and therefore the TCA cycle if you've already got a lot of ATP. Likewise, NADH and FADH2 will have negative feedback and inhibit the TCA cycle because if you already have them, you don't need to make more of them. This should be fairly obvious. So please memorize what stimulates and what inhibits the TCA cycle. That's everything that's important, as well as what stimulates and what inhibits the TCA cycle. But just for completeness sake, I'm going to draw in the rest of the enzymes that catalyze this reaction. Citrate synthase is what makes citrate. And think about it. The enzyme is literally called citrate synthase. So it's synthesizing or synthasing citrate. Citrate goes to isocitrate. That is done by aconitase. Alpha-ketoglutarate to succinyl-CoA by alpha-ketoglutarate dehydrogenase. Again, look at the name. It's dehydrogenating alpha-ketoglutarate. So obviously, this enzyme works on the substrate alpha-ketoglutarate. Succinyl-CoA goes to succinate from succinate thiokinase. Succinate goes to fumarate from succinate dehydrogenase. Again, look at the name. It's dehydrogenating succinate, so it's obviously acting on succinate. Fumarate goes to malate from fumarase, and ace means to break down, so it's acing the fumarate, or it's fumarasing, so it obviously acts on fumarate. And then malate goes to oxaloacetate from malate dehydrogenase. So if you look at the names of these enzymes, it's rather simple. And you know which enzymes go in here. It doesn't matter if you know exactly where they go, but if you know their names, you know what they act on. Very, very simple. Let's keep this simple. Keep the big picture in mind. Now, something else that's high yield is to know again where the NADH is produced and where the FADH is produced. And I've drawn them in here. Let's talk about NADH first. So NADH starts with the letter N, and all of the steps that produce NADH have reactants that are in the middle of the alphabet around the letter N. So look at this. I for isocitrate, K for ketoglutarate, and M for malate. They're all relatively around the letter N in the alphabet. But look at what the other steps begin with. So citrate begins with the C. That's in the very beginning of the alphabet. So clearly that's not around the letter N. Oxaloacetate begins with the letter O. And, that's sort of around the letter N, but it's, classically thought of as the end of the alphabet. So it's not quite right. Succinate begins with the letter S. Succinyl-CoA begins with the letter S. That's too far back at the end of the alphabet. So it's I, K, and M that generate the NADH. Now, I understand that the letter O is technically close to the letter N, but remember, when you think about where the letter O is in the alphabet, you classically associate it with the end of the alphabet. But when you think about where the letter N and the letter M and the letter K and even the letter I is, it's kind of the middle. So I know that's not a perfect mnemonic, but it's something to help you remember where NADH is generated. So again, all of the steps that start with the letter that's around the letter N, if you have to guess, that's where the NADH is produced. Now, as far as where the FADH is produced, it's rather simple. It's the equation or the step that generates fumarate is going to be the one that generates FADH. So the F's go together. So where you form fumarate, you form FADH2, and the F's just go together.